Hello, everyone. This section is an introduction to concrete technology, a part of the subject CVE 236, Civil Engineering Materials. In this section, I will talk about the definition, basic properties of materials to produce concrete, and type of concrete as well as its application. The outline of this section includes the following topics. First, what is concrete? In this topic, I will explain the definition of concrete in terms of civil engineering. Next, the components of concrete. This topic presents the raw materials used to produce concrete and how they are used in the construction industry. Then advantages and disadvantages of concrete as compared to other civil engineering materials such as steel and wood. After that, the basic properties of concrete such as workability in terms of slump and mechanical properties in terms of strength. Finally, the types of concrete used in Thailand and globally. What is concrete? Generally, concrete is an artificial stone or a composite material made of sand and rock that are bound together with a binding agent. In civil engineering, concrete is one of the most widely used construction materials. It is commonly used as the main material to build houses, roads, bridges, and other structures in many countries around the world. It replaces the wide usage of steel and wood. The basic components of concrete are sand, known as fine aggregate, and rock, known as coarse aggregate, which are bound together with cement and water to form a semi-homogeneous material. In its fresh state, concrete can be easily placed and poured into any shape, depending on the formwork. While that of in the hardened state, concrete is very strong and highly durable against weathering actions such as wind, sun, water, and even chemical attack. According to statistics from the Portland Cement Association of known as PCA, approximately 45 million tons of concrete are produced worldwide each year, or around 5.8 tons per person annually. In Thailand, at least 45 million tons of concrete are produced annually, which accounts for about 0.1% of global concrete production. This means that Thai people consume about 0.6 tons of concrete per person per year. This number is increasing every year due to the growth of the construction industry. Typically, cement is produced from two main types of natural resources. The first one is calcareous material, which contains a high amount of calcium oxide, such as limestone. The second one is argillaceous material, which contains significant amounts of silica and alumina oxides, such as clay. These materials are processed and burned at very high temperatures, up to 1,400 to 1,500 degrees Celsius, in order to produce cement clinker, and then it is ground into powder form. It should be noted that cement production consumes a large amount of natural resources and energy. Unfortunately, it also releases a significant amount of greenhouse gases, mainly carbon dioxide or CO2, into the atmosphere. This is because during the burning process, calcium carbonate or limestone is converted into lime or calcium oxide, which is the main chemical component of cement. And CO2 is released as a byproduct of this reaction. Approximately 0.5 to 0.7 tons of CO2 are emitted for every 1 ton of cement produced. This is a very high value, and therefore, many researchers are exploring alternative materials for concrete production. However, Cement remains the primary binder used in concrete today. In addition to cement, natural materials like sand and rock are also consumed during concrete production, which is why concrete technology is an essential subject that must be studied. Components of concrete, generally conventional or ordinary concrete, is composed of four main ingredients such as cement, water, sand, which we call the fine aggregate, and gravel or crushed rock, which is the coarse aggregate. When cement is mixed with water, it forms what is known as cement paste, which can be used for surface finishing or repair. When fine aggregate or sand is added into the cement paste, the mixture becomes mortar, commonly used in plastering and brickwork. Finally, when coarse aggregate or rock is added into mortar, the result is conventional concrete, which is used as the primary material in constructing structural elements such as columns, beams, slabs, and foundations. In general, concrete consists of 25 to 30% cement paste and 70 to 75% aggregate by volume. Therefore, the quality of concrete greatly depends on the quality of sand and rock used as aggregates. In the case of special concrete, additional materials are introduced or the mixed proportions are adjusted to enhance certain properties. These added substances are known as chemical and mineral admixtures. Chemical admixtures can speed up or slow down the setting time, increase workability, or enhance the durability of concrete, depending on the project needs. For smart concrete, which refers to next generation concrete designed with advanced functionalities. One good example is 3D printing concrete, which use modern 3D printing technologies and innovative materials to produce complex structures without traditional formwork. 3D printing concrete is a new way of building structures by using a special machine that prints concrete layer by layer. 3D printing concrete can save time, reduce labor, and create complex shapes that are hard to build with normal construction. It is already being used to build small houses, walls, benches, and even bridges. However, 3D printing concrete still faces some challenges, like controlling the material quality, working with steel reinforcement, and printing larger buildings safely. Another advanced example is self-healing concrete, which incorporate bacteria or some chemical admixtures that activate when cracks form in the concrete, allowing the material to repair itself. Next, let's now discuss the advantages and disadvantages of concrete. The first advantage is that the raw materials used to produce cement and aggregates are widely available in most regions, especially in Thailand. Additionally, the cost of raw materials for producing concrete is relatively low when compared to other construction materials like wood and steel. Another advantage is that the strength of concrete can be customized by adjusting the mix proportions. For example, high-rise buildings require higher compressive strength than houses or roads. By increasing the cement content and reducing the water content in the mixtures, the compressive strength can be significantly improved. Moreover, in its fresh state, concrete can be poured and shaped easily according to the formwork used, as shown in the accompanying slide. Concrete is also more durable than other materials such as steel and timber, which reduce long-term maintenance costs. In terms of fire resistance, concrete performs better than wood. For instance, wood can lose up to 80% of its strength at 300 degrees Celsius. whereas concrete retains up to 50% of its strength even at 500 degrees Celsius. However, concrete also has disadvantages. First, concrete is a brittle material, and its major weakness lies in its low tensile strength. This is why steel reinforcement is necessary in most concrete structures to improve tensile capacity. Concrete also requires a long curing time, typically 28 days, to reach its full strength. Another drawback is the heavy weight of concrete. Its density is approximately to 400 kilograms per cubic meter, which is much higher than that of wood, which ranges from 500 to 0 kilograms per cubic meter depending on the type of wood. Basic properties of concrete. Two basic properties of concrete are discussed in this section, which are workability, evaluated by using the slump test method, and mechanical properties, especially compressive strength. The slump test is a widely used and simple method to evaluate the consistency and workability of fresh concrete. The test involves filling a slump cone with fresh concrete, then tamping by steel rod about 25 times for 3 layers and lifting the cone vertically. The difference in height between the original and settled concrete is measured to determine the slump as shown in the picture. Slump is not only an indicator of workability but also reflects the mixed characteristics and quality of the concrete. There are three main types of slump. One, collapse slump. This indicates that the concrete mix is too wet or has too much water. It may lead to segregation where materials separate during placement. Two, shear slump. This type indicates that the mix has too much coarse aggregate and insufficient paste. It results in a dry and harsh mixture. 3. Two slump. This is the most desirable type, indicating a well-proportioned mix with good workability. For the hardened concrete, concrete strength is the most important property for determining the quality of concrete because of the most other properties are directly related to it. Generally, the higher the strength, the better the durability of the concrete. The generally strength of concrete include compressive strength. Compressive strength is crucial for structural design. It is measured using either cube samples, common in many standards, or cylindrical samples used in American standards. The sample is placed in a compression testing machine and the ultimate load is recorded. The compressive strength is calculated by dividing this load by the cross-sectional area of the sample. Results are expressed in units such as PSI or pounds per square inch, MPa megapascal, KSC or kilograms per square centimeters. Tensile strength. The tensile strength of concrete is significantly lower than its compressive strength, typically ranging from 8% to 15% of its compressive strength. This means that while concrete is strong under compression, it is relatively weak when subjected to tension. Modulus of elasticity, the modulus of elasticity of concrete, also known as Young's modulus, is a measure of its stiffness and its ability to deform elastically under stress. It's a crucial property for analyzing concrete structures and predicting their behavior under load. For design purposes, a linear elastic material, particularly for stresses below the proportional limit, is commonly used. In this class, I will focus mainly on compressive strength. For more details such as test method, standard, and calculation process about tensile strength, and modulus of elasticity will be explained in the laboratory session. Next is the factors affecting the strength of concrete. There are two main factors affecting the strength of concrete. One is water to cement ratio. The lower the water to cement ratio, the higher the compressive strength. However, reducing the water content also decreases the workability of the concrete. In such cases, more compaction effort or admixtures are required to improve fluidity. To its time, it is well known that the strength of concrete increases over time. In the early stages before 7 days, strength is relatively low, but by 28 days, concrete typically reaches about 80% of its full strength. This is why the 28-day strength is commonly used as a reference in most construction projects. Types of concrete. Nowadays, concrete can be classified into various types depending on uh, the design of the structure, the purpose of the concrete application, and the type of binder used in the mixture. Uh, for according to structural design, we classify concrete as reinforced concrete. This type is reinforced with steel bars to resist tensile forces. It is commonly used for column beams and slabs in houses, low-rise buildings, and general load-bearing structures. Pre-stressed concrete. Pre-stressed concrete is used in various buildings and bridges. It allows for longer spans, reduced thickness, and material savings. High tensile steel is tensioned before or during casting to apply initial compression. This compression counteracts future tensile forces, improving the overall performance. It should be noted that both reinforced concrete and prestressed concrete use steel inside to make them stronger. In reinforced concrete, steel bars are placed inside the concrete to help carry tension, uh, but they only start working after small cracks appear in the concrete. In prestressed concrete, the steel is pulled tight before the concrete is used. This pulls the concrete together, adding pressure that helps it resist cracking even before any real loads are applied. That's why prestressed concrete can be used to build longer, thinner, and stronger structures like bridges and parts of tall buildings. However, prestressed concrete more complicated and expensive to make because it needs special equipment and careful construction. A typical example is precast girders for long span bridges as shown in the picture. For according to the purpose of application, we classify concrete as high strength concrete defined by the American Concrete Institute or AC as concrete with a compressive strength greater than 55 megapascal. It offers improved mechanical and durability properties. This concrete is produced by carefully selecting materials, optimizing mix designs, and controlling the water to cement ratio as low as possible, often incorporating chemical admixtures such as superplasticizer in order to improve workability of concrete. Additionally, supplementary cementitious materials like silica foam and fly ash may be used to enhance compressive strength both early age and long term. High strength concrete is often used in high rise buildings and bridge structures in mega projects. The picture in this slide shows the Burj Khalifa, which is one of very famous high rise building in Dubai. A specialized concrete mix was developed with a compressive strength of up to 150 megapascal for this building to ensure the structural integrity of building. Self-compacting concrete, or sometimes it's called as SCC. SCC is highly flowable concrete and can be used to fill complex formwork under its own weight without vibration. It is suitable for areas with dense steel reinforcement or complicated shapes. The video clip shown in this slide demonstrates SCC developed at the concrete laboratory in KMUTT. This concrete exhibits very high fluidity, low viscosity, and no segregation. It is also clearly seen from the picture that no bleeding of water on the concrete surface, and concrete is very homogeneous matrix. Roller compacted concrete, or called as RCC. RCC is characterized by zero slump and is compacted using heavy rollers. It is mainly used for dams, sub-base layers, and off-road pavements. Lightweight concrete. Lightweight concrete has a density of 400 to 800 kilograms per cubic meters, much lower than normal concrete, which is 400 kilograms per cubic meters, offering benefits like reduced structural weight and improved insulation of concrete. The lightweight concrete is typically produced by using lightweight aggregates such as expanded clay and EPS foam bead or air foaming agents as shown in the picture. It helps reduce overall weights of building and is suitable for applications where weight reduction is critical. However, the strength of lightweight concrete is generally lower than that of normal weight concrete due to its higher void content. Pervious concrete or porous concrete, also called purpose concrete. It has high porosity or large void, allowing water to flow through the concrete. This concrete typically contains no fine aggregate. This type is useful in parking lots, urban lawns, and pedestrian walkways to reduce runoff from stormwater. Although pervious concrete offers significant benefits for stormwater management, it faced several challenges such as clogging, raveling, and reduced strength as compared to conventional concrete. These limitations can adversely affect its long-term performance and restrict its use in certain applications. Additionally, clogging will reduce the permeability and drainage capacity of concrete, potentially leading to ponding and reduced effectiveness. The picture and video clip show porous concrete developed at the KMUTT Concrete Laboratory. This mix has a compressive strength of about 40 megapascal and a water flow rate of approximately 1 liter per second, which are enough for use as urban road pavement. The last one is fiber reinforced concrete. This concrete contains fiber materials to improve flexural and tensile strength, which is the main pain point of concrete, making it less brittle and more ductile than conventional concrete. Fibers may be made from steel, glass, synthetic, or natural materials. The image in this slide illustrates a sample of fiber reinforced concrete. It shows that many types of fiber in terms of shapes and materials can be used in the concrete in practical applications. It is clearly seen that the concrete has more ductile than the concrete without fiber. Fiber reinforced concrete does not exhibit sudden failure due to the bridging effect of the fibers. Thank you for your attention and for watching. I hope this session gave you an understanding of the basic knowledge of concrete technology. For more information, feel free to visit the Concrete KMUTT laboratory. You can also contact me through many online platforms by scanning the QR code provided. Keep exploring and see you next time.